So hello and good morning. Welcome to day 3 of Monitorama. And topic for this session is tracing service dependencies at Salesforce. Oops. So I'm Sudeep Kumar. I'm a principal engineer within the monitoring cloud organization. So our organization provides a one-stop solution for all the observability needs within Salesforce. So we have platforms or in-house built platforms for logs, metrics, traces, and events. We receive millions of telemetry signals every minute, and we are responsible for monitoring the health and performance of thousands and thousands of applications spread across different regions, infrastructure, application stacks. And you can imagine at the scale of Salesforce how challenging it could be to handle so many services, right? And that kind of provides a good segue into our problem statement, which is relating to the curse of microservices. I mean, there are so many microservices. People are just looking at an excuse to create one sometimes. And I know people creating hello world applications with microservices and they keep it running in their production environments for some reason. But having said all that, the architecture has actually served us well, right? For so many years now in terms of how we scale out features independently, how we keep good separation of concerns, and all the goodies that come with the microservice architecture. However, it has its own set of drawbacks, right? Now, multiple teams own multiple services, so tracking dependencies across teams is quite hard, and these service interactions are never static. They evolve, they change over the period of time, and it is important to track them as well. And defining SLOs for services can be challenging. For example, I have seen so many cases where a service declares itself as a tier 1 high available service with finite availability, only to realize later on that they have taken a critical dependency on a tier 3 service with lower availability. I mean, and when something like this is discovered, it can be quite embarrassing, right? And there's not a real easy way to drill down into problematic inter-service dependencies. While metrics provides you a certain view, but it's not very granular enough. And identifying macro level transaction patterns such as for your errors, latencies can be useful, but missing when you are looking at external service calls. Now, how did we infer service dependencies? This is awkward to say the least. So we kind of have a repo where service owner would come and say, this is my service and I take dependencies on these services. You can quickly see the problem with that, right? It gets outdated pretty quickly and is often not representative of what's actually happening in your environment. And whenever such an incident happens, what we end up doing is we'll go to the service owner or the team and look for tribal knowledge to see whether do you know who are you talking to, and oftentimes they also are not aware. And people do some very interesting techniques as well. They look at firewall rules. They look at access policies to see whether you have opened up access from one service to another and try to just say that, oh, these services may be talking to each other, which again may or may not be true. And this is where distributed tracing can really shine, right? You can look at different kind of request flows, aggregate them uniquely, and be able to derive a meaningful service dependency graph. Not only can you depict a service dependency graph, but also you can look at the health of their interactions and possibly get to a more drill down view of a request flow. And during the talk today, I will cover the topic on what service dependencies means for an enterprise company like Salesforce, what are the different assumptions that we have taken, and what kind of experience are we providing to our users. Now, how does distributed tracing help with service dependencies? It answers very basic questions like how are my services used? How can I track downstream dependent services, the health of them? Can I discover unwanted, unsafe access patterns? Once you have this dependency graph drawn, it's much more easier to look at patterns, especially unsafe ones. Why is this service talking to a secure environment? Things like that. And you can understand the bottlenecks on service boundaries, which is often missing, and use that information to reduce the time to remediate on inter-service calls. Now, the building block for all this is the assumption that you are able to support tracing everywhere, right? And we have worked quite hard to be able to support in all kind of environments, all kind of regions, all kind of application stacks. So a lot of investment went there before we could actually get to the stage where we can start plotting the service dependencies. A little bit on our platform, like it's been around for a while, but more recently it has got a lot of traction within Salesforce, wherein we provide now distributed tracing for all of our services. It is a centralized collection of traces, and there are reasons why we have to go that way, because we have calls going from one region to another, and we want to be able to track them. Although there is a more recent push to be geolocal, and that's kind of a buzzword these days mostly. But if you look at different kind of telemetry signals that we collect from, we collect trace signals from APM agent. We have custom trace instrumentation for steel thread use cases that are often revenue impacting. We have managed frameworks where tracing is always enabled, and our mesh infrastructure is always enabled with traces with 1% sampling, and especially useful for our applications working on Kubernetes workload. Our tracing infra is also very tightly integrated with integration test, which kind of represents the health of critical user journeys that happen on Salesforce. And this is where we have been able to drive a lot of adoption for tracing. And this is something very useful for us in terms of getting visibility into the request flow health. Some numbers, we ingest around 300 million spans every minute. We see about 100 million unique traces reported every minute, and we also generate a lot of time series from these trace records, and which are very transaction aware, which your metric cannot give, right? Especially create a time series for a service call which started from this service and it ended up with this service. Things like that you can do with our platform, and that has been pretty useful when people have created alerts on it. Now, just I'm touching on distributed tracing semantics because I've heard so many definitions of a span in the last 2 days, including spans being a structured log to being an event. So I just thought I'll just introduce tracing in context of service dependency flow. So what is a trace? Trace is a request flow that moves across different services to attain a common goal, right? And each trace can be uniquely identified by a GUID, or you commonly refer it as a trace ID, and you have n number of spans associated with it. If you can consider this particular trace flow where it's just going between different services from S1 to S5, they have their own set of spans emitted. For example, S1 has A, D, and H, and each of these spans have few characteristics, right? It represents the operation that it performed, what is the start time of the span, and what is the duration for the particular span. You can use those span information and represent a trace waterfall view like this, wherein you start placing the root span, under which you will start placing all the child span and kind of create this hierarchical view. And if you consider x as your time axis, then x axis as your time, then the placement of the span is based on the start time, and the width of the span is basically the duration of the span. And this is, whenever you think of a trace, this is the view that comes to your mind, right? Nice waterfall view. And this is probably what you implement as part of get trace by ID calls like that. This is important with respect to service dependency, that how does context gets propagated across services. Now we use transport headers to be able to propagate trace context. If you are using something like database, there will be message headers involved. But the basic idea is that when a service call happens from app 1 to app 2, you kind of pass in the trace context as part of headers, and the app 1 would start a trace and it will emit the initial root span, will also influence the sampling that needs to be applied on that trace flow, which your application 2 would honor, right, and create set of spans associated with the same trace ID. And again, all these spans from both app and app 1 and app 2 are sent independently, and they are collected on a common trace pipeline and subsequently arrive at your tracer backend, right? Now, how do you use all this information to generate directed dependency graphs, right? Before we even go deeper there, we had few considerations to make. One, is there a need to build a trace context, right? I mean, we for the most part have been quite stateless in terms of how we handle trace data, as they arrived. We kind of ingested them without creating trace sessions. But clearly for this particular feature, there was a need to create a trace sessions. Now you could either do it during your ingestion time or you could do it during your query time. We decided to do it during the ingestion time because our storage was quite limiting in terms of what it could do. Oops. And do you really need 100% of traces to infer service dependency? Probably not. In previous talks, so many talks, you've seen that even with 1% sampling or 10% sampling, you can get a shape of a graph, and that is quite enough. And we at our end is currently doing 10% of sampling, but I think we can probably go lower. But that's what we are doing currently. And do you need to collect all the spans within the trace context? Now, as you're building trace context, remember you are keeping most of these traces in memory. So do you want to keep all all the spans associated with the trace? Probably not, right? You can uniquely identify the span based on things like span kind, which indicates whether it's a client span or a server span, or you can look at few attributes to decide whether these are boundary spans, right? And you only keep the boundary spans as you create a trace session. Now, both point 2 and point 3 feeds into whether we can do it in a cost-effective manner, but also an important consideration for us was, can we use existing managed stack? Because we wanted to build this feature, but at the same time, we didn't want to maintain the infra for it, right? So we looked at what we could use, which is already a managed stack within the organization, and that is something everybody should consider. So we had a managed platform for Flink, we had a managed platform for events, which basically uses Druid in the backend. So we decided to leverage those, fully understanding that there will be some capabilities that we will not be able to address for service dependency map, but which was okay. That's a kind of trade-off that we took. And what kind of sampling would work well, right? We briefly tested about parent-based sampling, but you need to be more diverse in terms of what kind of samples you collect from the source. So a little bit of adaptive sampling would always help, and that's what we tried to use it at the source to be more diverse about different transactions. And how useful are the red metrics? Right? Now you can generate a lot of red metrics with the sample data, but does it really speak the story? Based on our experience on a macro level, the shape of the graph that the tracing red metrics gives often gives you the underlying, often can point you to the underlying problems. It really doesn't give you, you can't really find needle in a haystack kind of a problem, but the shape of the graph at a macro level indicates there is something going on with your system. And do you need fully transaction map? While that is desirable, as a service owner, you are really interested in looking at the dependencies that you're taking on, like who are you dependent on and who is depending on you, right? So we had these key considerations to make. Based on that, we decided to transform our waterfall model to a dependency graph like this, wherein you will look at common traces, aggregate them, and create a dependency graph like the one that we have shown on the right. So if you look at the same operation create account, which had so many operations on it, finally you get a view like this, wherein service 1 talks to service 2, service 1 also talks to service 3, S1 to S5, S3 to S4. Now, is it enough, right? It doesn't really give you much other than they are talking to each other. You need to get more granular, right? And that's where you need to provide a context on what operation was actually involved when invoking that service. So we can get to a more granular view wherein you can say the auth operation is the one that is depending on S2 within service S1, and the search operation within S1 is what is depending on S3 and so forth. And finally, if you look at it, what does a dependency graph mean, right? It is just a collection of nodes and edges, right? And you can have your own definition of a node. For us, a node is nothing but a service with certain attributes. For us, it is service, subservice, which is more granular form of identifying a service. Operation, which is basically the same create account transaction that we saw in the previous slide. And the scope, which generally indicates where did the span arrive from, which data center and region. And you can then draw dependency edges between the nodes, which kind of shows the relationship. Right? This is kind of the pipeline we've ended up creating for enabling service dependency flow, wherein we have a collection of trace streams coming in. We had a Flink infrastructure that we maintained with set of our own custom operators. We initially would filter all the traces. We would sample them, split the trace by different trace IDs, and then we have this edge producers which will keep a trace session alive for a certain period of time, and then would emit edges, which is the most important thing here, right? And as it emits edges, they are in the most granular form. Now, you don't want it to be in the most granular form because it would mean that you have too many records going in as events, which would in turn affect your query performance. So we end up doing aggregation of these common edges and write them onto a data bus. In our case, it's Kafka. From there, a consumer would consume and write it to our backend event store. Once these edges are available on the event store, you can consume the data in different ways. You can use superset to slice and dice the data as you want. You can also depict the entire edges as a time series via Grafana. And we also have a custom API that we have exposed, which kind of will show you the entire service dependency graph. Now, another thing to keep in mind is how you can use edges to actually create an entire transaction dependency. For example, consider this particular trace flow where service A is calling service B calls service C, and service B also calls service D. You might be wanting to see the entire service dependency map starting from the root operation, say create account. How do you do that, right? So in the most granular form, you can consider the dependency edges as in this form of this table, wherein you'll have a source and a destination. But what we ended up also doing is anchoring these edges or records to a root service. So once you do that, you can just query the table and then ask that give me all the edges starting for this particular root service and operation, and based on that you can now plot a service dependency graph. And you can do other interesting things, right? For example, the same create account, you can have generally what you have. You generally have a time series that represents how that transaction has been doing, but really doesn't speak about where is it that you're taking a lot of your time. Now, if you have traces for that particular transaction, you can again now aggregate them, right? And provide a view like this to say that where is it spending most of its time. You can see here it's spending a lot of time in authentication, which is probably weird and something to optimize, right? And then something else that you can do is to look at adjacent dependency edges. So as a service owner, you want to immediately look up your left dependencies and right dependencies, that is who are you dependent on and who is taking dependency on you. Again, you can query the same table with the providing give me records which the destination service as the service B, and again source service as service B. Then you can again aggregate them and provide the same service dependency map visualization. Now, how do you visualize these dependencies, right? This is the experience that we are given. Sorry for the resolution, it's not that great, but the idea is that you can select a service, you select a subservice, environment, what kind of substrate you use, what kind of region, and then you provide time. Now, time is interesting, right? Because it's a dynamic service map. Now, what you can do is you can compare week over week. You can set up alerts to look at whether you had any new service dependencies show up, or whether you lost a service dependency edge. So things like that it kind of enables, because it's always a running service map. And essentially the entire graph is nodes connected with each other, and then the arrows represent the health. If it is green, then it is healthy, and then if you have red, that's where you had some problems, right? And if you look at this particular service, Druid routers, if you click on it, it kind of takes you to this particular view, which kind of shows you the metrics associated with that particular service, which is unsampled. At the same time, you can also see the tier the service belongs to, what is their PagerDuty page, Slack, how to reach out to them, and so forth, right? And this is pretty powerful whenever an event occurs. And additionally, if you look at the edge, they are annotated with certain numerics here, right? You can see 3.54K request that was made from this service to this service, but also it shows that there were a lot of unhealthy edges, right? 4% of them were unhealthy, and the average duration was 145 milliseconds. Now you want to get to a more drill down view of this. So what you could do is to expand that particular node, and that provides you a view like this, wherein it says that, okay, for the call from on-cloud events to the Druid routers, you had two kind of operations that were involved. Get calls were all healthy, but then there were calls to post which were kind of unhealthy. And we also show the set of traces that are associated with that particular flow from where you can get to the same waterfall view. Right? So you're organically leading people to a waterfall view from a dependency graph, which we found that people really love. How to increase trace coverage, right? And this has been often a tough nut to crack. Now we have done trace coverage, increased trace coverage by APM agents, wherein we have used auto instrumentation whenever possible. We have also had custom instrumentation done within the code, and this is often done for steel thread use cases. Again, the ones that are revenue impacting potentially, and where we add custom business logic spans and we annotate those spans better to get a good view of the entire request flow. Other than that, we have also enabled tracing on the service mesh by default and allowed that header and made sure the header propagation always works through our base framework code. We have increased coverage by utilizing traces in integration test suites. Often this has helped with risk assessment for new feature rollouts. So as feature rollouts, we look at how healthy the trace looks, and based on that we can decide whether we want to roll back that particular deployment or not. And prompt service owners generally to onboard to tracing, but what we often found is that just keep tracing on, right, by default, unless they explicitly choose not to do that for whatever reasons, right? Now, before I conclude, one of the things I wanted to cover is how do we detect broken traces, right? Now, what we saw that initially as we rolled out the feature, a lot of the nodes in our dependency graph were missing, and that probably meant that we didn't have good coverage, right? And often this feedback came from our end users, and we really didn't have a way to quantify it. So what we decided is to have a parallel pipeline which looks at 1% of the traffic and looks at the intermediate spans in a trace which is broken. Well, you can't really find out what if you are missing a leaf span, right? But you can always find out a missing span in the middle of a trace. So we looked at that, and we also looked at traces that had missing root span, and that happens for some legacy reasons. And we kind of saw a lot of patterns in our infrastructure, and we use those patterns really to be able to reach out to owners, reach out to service owners, make them their fix. Sometimes these were due to infra level config issues which we were able to easily identify. And one more interesting thing we ended up doing with by detecting broken traces is to mend the trace. So sometimes it could happen that you really didn't record a trace, right? Record a span in the trace, but you can look at historic patterns and see that, okay, this operation on this service is always calling this operation on this service. So potentially you can just insert that span in the waterfall and not really break the trace view, right? So we are trying to do whatever we can to give a more delightful experience, even if some of the data in the tracing is missed. Now, before I conclude, I wanted to say that we just rolled out this feature in a month or so, and we didn't really expect much, but the amount of interest that we have seen upon rolling this out was phenomenal, and people have been always reaching back to us, giving feedback, which was something we always missed before. This is a good way by which we have increased tracer adoption within the company, and something everybody should strive doing. With that, I'd like to conclude my talk, but thank you, everyone. Repeat.
It's hilarious timing because I sat down and I was like, there's something in my shoe. I think I got time. Let me just take my shoe off real quick and get that rock out of there. Then I hear clapping and I'm like, how did I know this was going to happen? All right, great. Are there any questions? Yeah, right here.
What's the retention for the data, and then do you do any like day over day or week statistics?
The rejection of data?
What's the retention?
Oh, retention. Oh, so we retain the data for 30 days currently, and it's mostly aggregated data. So the cost is not as much. And what was the second question? I'm sorry.
Do you do any any like day over day or week over week statistics?
Yes, we do, and that's
Any
a
day
view.
over day or week over week.
Yeah, and that's a view we kind of want to overlay in our visualization, where you kind of show the current trend versus the historic trend, and look at the delta in terms of if anything has changed, and people can make useful inference out of it.
Awesome. Any other questions? I've got one in the middle, Roy. Yeah, it's you. Sorry.
What is one of the most interesting or surprising dependencies?
What's the most interesting or surprising dependency?
So we had a lot of cyclic dependencies, which was very interesting, and people didn't realize it existed. And it was clearly an architectural miss for the most part, and it happened at some point in time. It did not originate in that way as services were built out, but over the period of time, as they looked at the graph, they realized that they're talking to each other, right? And that was weird, like for the most part. So that was some of the interesting things that we've seen with once we rolled this out. Yeah.
Yeah, Andrew.
So aside from like the 30 days of retention for the sample traces, are you tracking the graph over time? Are you doing like change graph sets to like see when things like that happen and then correlate them?
Are you
Yeah,
doing
so-
change graph sets and
Yeah, and that's a visualization we are currently building, wherein you can overlay that experience. But we already have people set up alerts around that, wherein they kind of look at the delta and then kind of raise the alert where they find a new dependency edge or they see something has been missed. So that capability exists, but we are still working on overlaying the historic trends with the current trend.
Yeah, right here.
How big infrastructure overhead to introduce it with enabling APM and tracing everywhere?
What was that? How big of an infrastructure?
Overhead.
How much infrastructure overhead for the APM?
So it's not much, surprisingly, and I think the main reason is because we only look at the sample set of traces. I would say the cost of this, when we did comparison, it was around 5% of our original cost of what we do for maintaining the entire tracing infrastructure. So it was a much lower overhead.
Any other questions? Any top? I think we're good.
I
Was
think
there one?
there's
Everyone's pointing. My goodness. Thank you.
So I saw that you stored the dependency by a source service and the destination service. How do you infer like integrate dependency? Like for example, like A might depend on B and B depends on C, but they might be under different trace context.
Yeah.
How do you know like A depends on C or not?
So that's why
So
I
how do you
said
handle
that-
transitive
Yeah,
dependencies?
it's not a fully transactional service map, right? That's one of, you can look at a fully transactional service map from the context of the root operation, like a create account, but you lose that granularity when you try to expand it from a service which is in the intermediate, somewhere in the intermediate hop of the service dependency graph, and you cannot really be context aware more than one hop, right? Literally, if you go beyond one hop, you kind of lose the context, which is a trade-off that we kind of took, because those, as I said before, we had some managed stacks that we wanted to leverage, and we fully understood that there will be some capabilities that we will lose, but we were kind of okay with it. And we are already seeing a lot of value from what we had built. So at some point, if we want to go that out, we will definitely be able to provide it. But right now, we don't see the need to do that.
So even the trace root is the same one, they might be under different trace context.
Yeah, beyond one hop, you would end up seeing it, which is fine for how you look at it, but that's kind of the offering that we give.
Awesome. Thank you so much, everyone. Let's give a big round of applause for Sudeep.